Well, hi everybody. I had been hoping to get a classroom and a whiteboard to be able to talk to you in my usual fashion up in front of a room, but unfortunately this is going to have to do. I've got some paper here and I'm going to try to write out some notes. Hopefully this is going to make sense and you'll be able to read the notes just in the same way that you normally would when I'm in class. You know, as always, of course, you're welcome to ask me questions. You can send me questions. Ask me next week when I get back if you'd like, and I'll do my best to help you out. We are going to talk about sections 13.6 and 13.7 in our book today. And just to kind of set that up, I want to remind you about what we were talking about in the earlier sections. We had been talking about calculating the mass of a lamina. A lamina is just a flat plate that sits in a two-dimensional plane, and the region that is occupied by that mass is often called R. And there is a density function that tells us at any given point xy, it tells us what the mass per area is on this lamina. That's denoted with rho of x and y. As we saw in the previous lesson, the way we would calculate the mass of this lamina as a whole is we would take that density function and we would do a double integration over the whole region R of that function. And so here's the symbolic way of writing that. The mass is the double integral of the density function times dA. But let's imagine now that we're actually talking about not a lamina that's sitting in the xy plane, but an actual three-dimensional solid body. And let's suppose we wanted to know the mass of a 3D solid body. We're kind of upping everything by one dimension when we do that and when we ask that question. And so how is this going to look? Well, for one thing, our density function is going to depend not just on x and y, but also on z. So our density function, let me just write this here, our density function is going to be rho of x, y, and z this time, okay? Because it depends on all three coordinates of our point. And this is no longer a mass per area. This would now be, in our new three-dimensional model, this would be a mass per volume that we're looking at. Okay? And how would we find the total mass of this entire three-dimensional solid object? Well, we're going to mimic what we did for the lamina in 2 dimensions. We're going to take the density function, rho of x, y, z, and we're going to, again, view that as a mass per volume. I'm going to multiply that by a little bit of volume. Now, instead of calling it dA, now I'm going to call it dV to emphasize that this is a volume rather than an area. When we multiply the density times the volume, we, of course, are going to obtain a little bit of the mass of this whole solid. But then what we're going to have to do is add up the contributions to that mass throughout the entire solid body. And that's going to involve an integral, but this is a new kind of integral this time. This is going to be a triple integral. So what I'm doing here with this example is I am motivating the next section, which is going to be triple integration. So you're going to see 3 integral signs. And instead of a region R in the xy plane, we're now going to refer to this solid region as Q. So this is the notation in our book. Q is going to be the region occupied by this solid body whose mass we are calculating. Okay? So it's a triple integral. It means we're going to have to set up 3 sets of limits of integration to do this kind of a problem. Okay? So this is the topic for section 13.6. It's called triple integrals. And it's a little bit more involved than the double integrals that we saw earlier in the chapter. but it's the same concept, but the visualization can sometimes be a little bit trickier. Okay? I think the easiest type of solid region to do a triple integral over is going to be a rectangular box. So if I have a box, let me set up the limits for a box. This is called a rectangular box, and this would be Q. This is the region that this box is sitting in. This would be a set of points, let's say x, y, and z, right, such that, well, x maybe is limited between a and b, and then let's say that y is limited between c and d, just like before when we had a rectangle. But now we have a z variable to take care of as well. Let's imagine that z is sandwiched between k and L. All right? If we had a box like that, then you won't be surprised that the limits of integration would be very simple. They would just be the constants, a and b, c and d, and k and L. So in this case, for a box, for a rectangular box, which is what we're talking about, this is the simplest possible way of having a triple integral problem. For a rectangular box, right, your triple integral, whatever it's representing, whether it's a mass of a solid body or any other triple integration that we might want to calculate, right, your triple integral of your function, now I'm just going to call it f of xyz instead of rho of xyz, right? This could be represented as the integral where x goes from a to b, and then another integral where y goes from c to d, and then finally the integral where z goes from k to L of f of xyz. And now we have to be careful with the differentials. The z is the inside integral, so I'm going to put dz on the inside, and then dy, and then dx. And I'm running out of room over here on the side, but that's dx. So this is dz, dy, dx. Okay, that's if you put x on the outside, y in the middle, and z on the inside. As you could imagine, and as we saw many times with double integrals earlier, if we have 3 sets of integrations to do, we can reverse the order, and in this case, there are actually 6 possible orders of integration. 6 possible orders of integration, right? And then this means we have more choices to wade through. So we could have, as I was showing in that last example, dz, dy, dx. That's how I set it up for the rectangular box. But we could also do dz, dx, dy. Or we could do dy, dz, dx. Or we could do dy, dx, dz. Or we could do dx, dz, dy. Or we could do dx, dy, dz. We have 6 different possibilities for the order of integration for a triple integral. And this definitely means that we have to think carefully about which of those 6 choices we're going to use on a given problem. As you can imagine, choosing which of those 6 orders of integration to use is closely tied to the function that you're integrating, as well as the shape of the region, or in this case the solid region, the 3-dimensional solid, that you're integrating over. Let me give you an example of a fairly common scenario of a type of shape, and how the order of integration would naturally set up for that type of shape. Before I do that, let me just mention that for a box, it really doesn't matter. You can do any one of these 6 orders of integration, and essentially the amount of work and the difficulty of the integration is going to be equivalent no matter which way you do it. Okay? But the point is that all 6 of these orders of integration will give you the correct answer. They'll give you the same answer, and this is just a theorem of Fubini's that we already were exposed to for double integrals, and now we're just extending it to triple integrals. Let me draw you a picture of a situation where we would have perhaps a preferred order of integration. So I'm going to draw my XYZ axes here. And by the way, if there's any questions, feel free to stop and pause or rewind what we're looking at here and give it a closer look if I'm going too fast. Let's imagine that we have a solid region that looks something like this. It's got sort of a triangular base, and then above it there's a triangular ceiling, and this is just forming kind of like a prism here. But then let's imagine that on the bottom of the solid it's actually curved according to some surface, and also on the top of the solid, let's imagine that the top of the solid also is curved according to some surface. I'm going to call the lower surface here, I'm going to call it phi1 of x and y. That, of course, is a z expression. The upper surface I'm going to call phi2 of x and y. So my solid region Q here occupies all of this space right in here, okay, that I'm shading in on this picture. It is entirely contained above this domain. I'm going to project down to the XY plane so that you can see again. I want you to be able to see that region that I drew it as a triangle, but of course it could be any shape whatsoever. Imagine that that is the sort of the shadow of the solid down in the XY plane. In fact, I could call that R. It's like a region. It's a two-dimensional region in the XY plane. Now, if I was going to set up a triple integral, let's say we had some function, let's say it's f of x, y, and z, and if I wanted to perform a triple integration over the whole entire solid Q, the way I would recommend that you think about that, guys, is think of it as the two integrals on the outside correspond to the xy region, which I've labeled as R in the picture, the xy region of integration. And then the inside integration would be the z variable. For this type of solid, that's going to make sense to do it that way. Because notice what you can do. You can say, look, if I stand anywhere in the region R and I look up above me, what do I see? Well, I see white space, white space, white space, white space, until I hit the lower surface. That's phi1 of x and y. That's where I'm going to start integrating, right? I start integrating at the lower surface, and I'm doing vertical tubes of volume here, essentially, that are above the region R. So I'm going to integrate, 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 all the way until I hit the upper surface, which is z equals phi2 of x and y. Okay, so you're integrating from the lower surface to the upper surface. It's a vertical integration in the z direction. Okay, my function is still the same, just f of x, y, z, but I'm doing the z integration first on the inside. Now, after I've done that z integration and evaluated it, the only variables that should be left in my integral would be x and y. And at that point, you're just looking at a double integral again. And we know how to do those. A double integral would, of course, be with respect to area. So I'll write that as dA right here. And you would just proceed as normal to set up the limits of integration for whatever the region R is that's the base here in the xy plane. The key thing to realize is that when you're doing a triple integral of a solid region kind of this nature, you want to think of it as two integrals on the outside, and then the inside integral is being explicitly set up differently on the inside. So in this case, the z variable. Now, if this whole solid region had been turned on its side, right? Imagine what would have happened if your region had been, you know, something like this, where you have, I don't know, let's assume we have like a disk here in the xz plane, okay, and above that disk you have some surface here, right, and then it becomes sort of the shadow of that cylinder going like this, and then some surface here. Well, this lower surface would be, you know, phi1 of x and z, and that would be a y variable. and the upper surface would be y equals phi 2 of x and z. In this case, you would want to set this one up with the x and the z on the outside and the y variable on the inside. Okay, so as with double integrals, sometimes there is a preferred order of integration. Whoops, this should be x and z here. Sometimes we prefer one order of integration over another. It really depends a lot on how this solid is oriented in your three-dimensional coordinate system. Okay? Normally, though, it's very common that the z is the inside variable and you're integrating x and y on the outside. Okay, so with that as a background, why don't we try an example? So let's do an example over here. Let's evaluate the following triple integral. Triple integral of, I'm going to call it just y dv over q, where q lies under the plane. It lies under the plane z equals x plus 2y, and above the region in the xy plane, above the region in the xy plane, bounded by the following curves: y equals x squared, y equals 0, and x equals 1. Okay, so there's a lot of equations there. The function that we're integrating is pretty harmless. It's just the function y, but I'm going to have to figure out how to set up this integral. In fact, evaluating the integral is almost a secondary issue to me in some sense. A lot of times, guys, I'm just going to be asking you to set up the integral. This means I'm going to give you the limits of integration. I'm going to ask you to give me the limits of integration for x, for y, and for z, in whatever order of integration you'd prefer to use. Okay? Now, it's going to be very difficult to actually draw this three-dimensional solid on your paper. The good news is that on a lot of these triple integral problems, you don't have to draw the picture of the whole three-dimensional solid. What I can say for sure is that my region is above the xy plane. Remember, the xy plane is just z equals 0. So it's above that, but below the plane z equals x plus 2y. You see, we have a lower limit and an upper limit for z that are already given to us in the problem. I'm going to put that z variable on the inside of this triple integral. Now, to figure out the x and y limits, I only need a two-dimensional picture. I'm going to draw some axes here. Remember to draw your axes very lightly so you don't confuse the region with the axes. So there's my xy plane, and I'm only going to draw the region in the xy plane. So y equals x squared, of course that's just your good old parabola. Right there is y equals x squared. And then we also have y equals 0, which is the x-axis here. So now I'm drawing it heavier. And then we have x equals 1, which I'm going to put right over here. Okay? So you can see the region is right there. That bounded shape on the xy plane. So if I would like to set up this integral now, I'm going to write it as a triple integral of y dv over the region Q. And again, I'm going to think of the outside two integrals as being the region, that's this region R right here. Okay, and then on the inside, I'm going to integrate z. My function is still y, and then I'm going to have dz, and then I've got to decide on the outside integral what order of integration to use. Okay, but notice that z is going to go from 0 up to the plane x plus 2y. The solid region is bounded between those two planes. So those two planes are going to be the lower and upper limits of the integration. For the outside limits, I'm going to go back to double integrals. We learned how to do double integrals earlier. All we're going to do here is decide which one to put on the outside. It doesn't matter too much on this problem. I'm just going to choose to put x on the outside. Notice that x starts here at the origin, and we go over to x equals 1. Okay? And then if I stand somewhere between 0 and 1 and I look at the y variable, I see that y starts at 0 and goes up to the parabola x squared. So my limits on y would be 0 and x squared. And so I'm choosing to do the integration in the order dz, dy, dx. Okay? Now, setting that up is, in my view, is the harder part. And so if I was a little fast there, this is a good place to pause and reevaluate what's going on. Notice I don't have a three-dimensional picture. I'm not trying to draw the whole solid. I've just got a picture of the region in the xy plane. And that's just two-dimensional, and I can handle that sketch pretty easily. And that sketch is helping me set up the outside two limits of integration. For the inside limits, I never used a picture at all. I just simply looked at the equations that I was given in the problem. Okay, so now, as usual, we can go ahead and evaluate this integral from the inside out. So the x integral is going to be last. That's on the outside. The y integral is in the middle, so I'll put that integral back down again. The very first integral I'm going to do is z. So notice that the y is a constant when I do that. And when I integrate dz from 0 to x plus 2y, I'm just going to get x plus 2y, right? Because I'm just going to get z, which I evaluate at the upper limit and the lower limit, and I subtract. It just gives me x plus 2y. And now I have dy and dx. Okay? So maybe before I go on, I can take a second and just clean that up a little bit here. So let's simplify the integrand. The new integrand is going to be xy plus 2y squared. And this is going to be dy and dx. And now I'm ready to do the y integration. Okay, so when I do the y integration, I'm once again going to leave the x on the outside. And when I integrate y, I'm going to get x y squared over 2 plus 2/3 of y cubed, which I have to evaluate from 0 to x squared before I go on. Okay, let me just move this over here. Hopefully you can still read that okay. I'm just going to continue my work right here. I have to evaluate, I now have to evaluate the upper and lower limits on y. Of course, when I plug in 0, I'm not going to get anything. So I'm just essentially plugging in x squared for y. I believe that's going to give me 1/2 of x to the 5th, right? Plus 2/3 of x to the 6th. And finally, I have to evaluate that integral. I'm going to get 1/12 of x to the 6th plus 2 over 21 x to the 7th from 0 to 1, and that's 1/12 plus 2 over 21. And if you simplify that, the answer is 5 over 28. Okay? So that is what we end up with for the final answer. I want to just look one more time at the setup of this integral and make another comment for you here. Notice the outside limits of integration, they have to be constant numbers. They have to be constants. The middle limit of integration doesn't have to be constant numbers, but notice that the y integration here only has x's in it. There's no z there. And that's because the x is integrated on the outside of the z. Okay? And finally, the inside limit of integration, which is z, can have both x and y in it. Okay, so the inner limits of integration can be anything involving the outer two limits of integration. Maybe I should write this down for you as a remark here. So just as a quick remark, okay, so let's just state this very carefully. The outer limits of integration must be constant. Those must be constants, okay, always. For any triple integral whatsoever, the outside limits of an integration will be constant. The middle limits of integration, okay, they don't have to be constant, but they can only depend on the outside limits, whatever variable is being integrated on the outside. So whatever that outside limit variable is, that can appear as a limit of integration on the middle integration. Okay, and finally, the inside limits of integration. Okay, here's where you can have both of the outer two variables occurring. So this can depend, there can be appearances of the outside two variables. Okay? It's really very important, I think, that you continue to be vigilant about writing. So just right here, you see how I wrote down x, y, and z, so I can see which variable is being integrated in which integral here? Because that can get confusing when you have so many different orders of integration that you can have. Okay. I just want to point out another quick little comment here. Again, feel free to rewind or pause as necessary. I just want to make a remark. So I was talking about a triple integral as representing the mass of a solid region, a three-dimensional solid. And so you do this triple integral of your density function. Of course, in this case, you would expect that to be a positive function for all points x, y, and z. Okay, so we're using we're using density with a triple integral to calculate the mass of a solid. However, so I can call this another remark, if the density function is just equal to 1, if it's just equal to 1, then of course what's that mean? That means that the mass per volume is equal to 1. In other words, in that case, the mass of Q is the same as the volume of Q, because the density is just 1. In other words, what we're saying here, guys, is that the volume of your solid region Q can be viewed as the triple integral of 1 dV. Okay? So you can calculate a volume by using a triple integral. Okay? You can calculate, and I'm going to come back to this point because I know that we were using double integrals to calculate volumes. So it can be a little confusing. I know that this was confusing for me when I first learned this material, that to calculate volumes, we sometimes are using a triple integral, and we're sometimes using a double integral. If you're using a triple integral to find the volume, you must be integrating the function 1. That's the point. Okay? Let's try it on an example, just to see how that would look on paper. Let's find the volume, and then I'm going to show you why the triple integral approach and the double integral approach really amount to the same thing. It doesn't really matter which way you view it. I'll set it up as a triple integral, though, since that's what we're talking about. Let's find the volume of the solid bounded by, let's find the volume of the solid bounded by the cylinder x equals y squared and the planes z equals 0 and x plus z equals 1. Okay. So in this case, again, we can kind of tell that, we have an equation for z right here. We have another equation which we could solve for z. And if we did all of that, we would hopefully be able to to find the lower and upper limits for z, right? So